Welcome to the deep dive. Our mission today, well, it's a crash course, really, in the future of computing. We're diving into the material science that might finally get us past the limits of silicon.
Yeah, it's a critical moment. For, 50 years? Microelectronics has been all about Moore's law.
Exactly. But that whole architecture, it's hitting a physical wall now. We're basically out of atoms to shrink down, especially for the core parts of the transistor.
That's absolutely right. I mean, when you push components down to just a few dozen atoms thick, classical physics starts to get really messy.
Leakage current just goes through the roof.
Totally insurmountable. And the materials we've relied on forever, like good old silicon dioxide, they're either too thick for the next generation or they just don't have the functions we need now.
So this isn't just like a minor upgrade.
Oh no, it's a fundamental pivot. We're talking about Oxide Electronics, multifunctional thin films. It's a whole new game.
And it pulls in everything, right? Chemistry, quantum physics.
Materials engineering, yeah. All focused on building these advanced devices that can maybe handle memory, computation, even sensing, all packed together.
Okay, so to tackle this massive shift, we're doing a deep dive. Our source material, it's a key text. Thin Films and Heterostructures for Oxide Electronics.
Right.
We're going chapter by chapter. Think of it like a treasure map for this new era of materials.
I like that, a treasure map.
Our goal is to pull out the most surprising stuff, the critical insights on, ferroelectrics, the whole high-K dielectric crisis, Spintronics, and the wild fabrication techniques needed to actually make these things.
And we have to get granular because the problems, the solutions, they happen at the atomic level. It's all in the details.
It's not just about listing fancy new materials.
No way. You have to understand the hurdles, thermodynamics, will it even stay stable? Interface quality, that's huge. Atomic stability. And we need to see the breakthroughs, the proof that these things might actually work in, real devices someday.
Okay, let's get into it then. We're starting right where the bottleneck is, fixing that fundamental building block, the insulator, the dielectric.
Yep. If the transistor switch doesn't work, nothing else matters.
All right, chapter 1 jumps right into nanoscale ferroelectrics and miniaturization. Now, for listeners, these materials, they're absolutely key for non-volatile memory, right?
Critical. Unlike your standard DRAM, which forgets everything when you cut the power.
Gone in an instant.
Ferroelectrics hold their polarization. That's their memory state. Power off, memory stays. But making them into ultra-thin films, that's where the trouble starts. Major problems crop up.
Okay, what kind of problems are we talking about?
Well, the source lays out like a gauntlet. 4 key challenges you absolutely have to solve all at once.
4, okay.
The first 2 are about stability when you use the device. First, fatigue. That's the material just breaking down, losing its ability to switch polarization after you cycle it many, many times.
Like it gets tired.
Pretty much. Often it's domain walls bumping into defects. Then there's imprint. That's the static version. The material starts to prefer one polarization state over the other. It gets stuck.
Making it hard to flip the switch back. So dynamic wear and static wear. What about just holding the memory?
That brings us to number 3, retention. Can it actually hold that charged state for a long time? Years, ideally. And closely related, number 4, polarization relaxation.
Okay, polarization relaxation, that sounds complex.
It is. It's this slow, gradual loss of the stored polarization without switching. The domains inside the material slowly rearrange themselves over time. It's a huge puzzle because it involves domain walls, defects, the crystal structure, all interacting at these tiny scales.
What kind of scales are we talking?
We're looking at, a few hundred to maybe a few thousand angstroms, around 10 to maybe 100 nanometers. Really, really small.
So you've got physics happening on this incredibly tiny scale. It's complicated, it's dynamic. To figure out this relaxation thing, you can't just look at the whole chunk of material. You need to see the domain walls themselves, right?
Precisely. And that's why the source really emphasizes the need for a very specific tool, unique, non-destructive, piezo response scanning force microscopy, or piezo response SFM.
Piezo response SFM, why is that the go-to tool here?
Because it's one of the few techniques that lets you actually probe the physics at those exact nanoscale dimensions, non-destructively.
Okay, let's break that down quickly. Piezo response SFM, it maps electrical domains using a mechanical signal. How does that work?
Yeah, basically, you take an atomic force microscope, right? Put a conductive coating on the sharp tip, bring that tip into contact with your ferroelectric film.
Okay.
Then you apply a small AC voltage to the tip. Now, because the material is ferroelectric, it's also piezoelectric, meaning it physically expands or contracts when you apply a voltage.
Ah, okay. So the voltage makes it wiggle.
Exactly, a tiny wiggle. The SFM tip senses this incredibly small mechanical movement. And the amplitude of that wiggle tells you how strong the local polarization is, and the phase tells you which way it's pointing, up or down.
It's like a nanoscale stethoscope listening to the memory cell breathe.
That's a great way to put it. And with this, researchers can literally watch domains relax over time, map out the 3D polarization vector, see exactly what's going on inside.
And having that visualization tool led to some serious breakthroughs in scaling these things down.
Oh yeah. The source highlights how advanced nanofabrication, specifically using a focused ion beam, or FIB, that was key.
FIB milling. That's like using ions to sandblast away material with atomic precision.
Essentially, yeah. They used it to cut the ferroelectric film into these tiny, isolated nanoscale capacitors, like little memory islands.
So the FID wasn't just for making the final device, it was crucial for testing the physics at the scale they needed to understand.
Exactly. It enabled these really quantitative observations. For instance, they could directly see the 90-degree domain structures in epitaxial films.
Those 90-degree domain walls.
They cause strain, right? Affects the switching.
They do. They create spontaneous strain. Sometimes you can even see tiny bumps on the surface because of them. And yeah, they definitely impact the hysteresis loop, the switching behavior. Understanding those internal boundaries is vital for stability.
But the really big news, the thing that showed scaling might actually work, was demonstrating that you could still get piezoelectricity, you could still get stable ferroelectric switching in capacitors just 70 nanometers by 70 nanometers.
70 nanometers. I mean, think how small that is. It proved the fundamental memory element works robustly even when shrunk down that far. It was, at the time, the smallest reported device where they had actually quantified all the key properties.
Huge proof of concept. But then Chapter 1 pivots. It starts talking about the future, about green ferroelectrics. What's driving that shift? Is it just about getting rid of lead and PZT?
That's the main driver, yeah. Toxicity. PZT, lead, zirconate, titanate, it works great. You can process it at relatively low temperatures, which is good for manufacturing, but it contains lead, which is obviously not great for the environment or health.
Exactly. So the push was find a replacement that performs just as well or better, but without the lead.
And the material stepping up in the source is bismuth ferrate, BiFeO3, BFO.
BFO looks really promising. It kind of nails the performance trade-offs. Its ferroelectric Curie temperature is incredibly high, like 800 degrees C. So it's stable way above any normal operating temp.
And the performance metrics. Polarization.
Massive spontaneous polarization, 90 microcoulombs per square centimeter. That gives you really strong, clear memory state.
And crucially for manufacturing, it can be integrated with standard silicon processes.
That's a big plus. It has a relatively low dielectric constant for ferroelectric, maybe 80 to 140, good structural stability, and critically, you can process it at lower temperatures, maybe down to 450 degrees C. That makes it much easier to integrate onto existing silicon CMOS chips.
And BFO has a bonus feature mentioned. It's multiferroic.
Yes. That means it has both ferroelectric order and magnetic order specifically, antiferromagnetic order coexisting in the same material.
Whoa, so potentially you could have electrical memory and magnetic effects in the same tiny block. That's real multifunctionality.
Exactly. But even BFO, even these advanced ferroelectrics, fundamentally they're insulators. And the quest to fix the main insulator in the transistor itself, the gate dielectric, that search for high-K materials, that was maybe the biggest material science scramble of the early 2000s.
Which brings us neatly to chapters 2 and 3. This focuses squarely on that immediate grand challenge, as the source calls it, finding a replacement for the gate dielectric in MOSFETs. This was Moore's law hitting the panic button.
Oh, it was absolutely an existential crisis for the industry. Your standard silicon dioxide, SiO2, has a dielectric constant K of just 3.9, fine for decades. But as transistors kept shrinking, the SO2 layer had to get thinner and thinner. Below about 10 angstroms, that's literally just a few layers of atoms, the leakage current just exploded. Quantum tunneling.
Electrons just punching right through the barrier.
Exactly. Which means wasted power, way too much heat. Your chip basically melts or drains the battery instantly. So the semiconductor industry, led by Intel at the time, set this hard deadline. Find a replacement material by 2007, or Moore's law stops. Dead.
Wow. That's intense pressure on the materials people. So what did this miracle replacement material need to do? The requirements list must have been insane.
Chapter 2 lays out 5 absolutely strict, non-negotiable requirements. It's a killer list.
Okay, let's hear them.
1, Obvious,
Right.
right? High K value, much higher than 3.9, so you can get the same capacitance with a physically thicker layer, cutting down that tunneling leakage.
Makes sense, too.
Thermal and chemical stability in direct contact with silicon. This is huge. It has to survive the chip manufacturing process, including a critical high-temperature anneal, often around 900 degrees Celsius.
Why is that 900-degree step so essential? Can't they just skip it?
Nope. That high-temperature step is needed to activate the dopants in the source and drain parts of the transistor. Without it, the transistor doesn't work properly. It's fundamental to CMO processing.
Okay, so a high K, stable with silicon at high temp. What else? 3.
High band gap. You need a wide energy gap, typically 4 to 5 electron volts, to intrinsically block leakage current. 4. Low defect density, what they call DER, right at that critical interface between the dielectric and the silicon channel. Defects there trap charge and kill performance.
And 5.
Achieving a low equivalent oxide thickness, or EOT, that's the bottom line metric.
Right, EOT, that's the thickness of good old SiO2 that would give you the same electrical effect as your new, physically thicker high K material.
Yeah.
They needed an EOT near 0, basically.
Precisely. Now, the first place they looked was materials already used in memory chips, like tantalum pentoxide, T2O55V5, or titanium dioxide, TO222. Complete failure. Spectacular failure, actually.
Why? What killed them?
Requirement number 2, stability with silicon. These materials are thermodynamically unstable when you put them right next to silicon and heat them up to 900 degrees.
Can you walk us through the physics of that instability? Why do they react?
It boils down to basic chemistry, Gibbs free energy. For the reaction between, say, Ta2O5 and silicon at high temp, the change in Gibbs free energy, delta deuterio, is negative.
Meaning the reaction just happens spontaneously.
Yes, it's energetically favorable. The silicon literally rips the oxygen away from the tantalum oxide.
So what forms at the interface? What's the nasty byproduct?
You get tantalum silicide, TanC22, which is metallic and bad for insulation, and critically, you form silicon dioxide, SiO22X.
The very low K material you were trying to replace.
Exactly. So you end up with this unwanted layer of low K SiO22 and silicide right at the crucial interface. Now, your gate stack capacitance is determined by these 2 layers in series, your high K layer and this unintended low K layer.
And the low K layer dominates, killing the whole point.
Completely nullifies the benefit. Your effective K value plummets. And the source makes a really important point here. In DRAM memory, you might stick a thin barrier metal layer in between to stop this reaction.
But you can't do that in a transistor.
Absolutely not. In a MOSFET, the gate dielectric needs to project the electric field through to the silicon channel underneath to switch the transistor on and off. If you put a metal barrier there, it shields the channel from the gate voltage. Your transistor stops working. You need direct, intimate, stable contact.
Wow. Okay, so that chemical instability wiped out the early contenders. This forced a massive, really systematic search effort, didn't it?
Oh, yeah. It was an incredibly thorough approach described in the source. Yeah. First, they went through the periodic table, analyzing the thermodynamic stability of all binary oxides and nitrides against silicon.
Everything.
Pretty much everything remotely plausible.
Right.
Any element whose oxide or nitride calculation showed a negative delta G(NI) for reaction with silicon at 900 C crossed off the list immediately.
Like, give me an example. Who got kicked out early?
Transition metals, like iron, for instance. All its common oxides, FeO, F3O4, Fe2O3, they all react readily with silicon. Gone. So you end up with this relatively short list of elements whose oxides might be stable.
Okay, so they have a short list of chemically compatible binary oxides. What's the next step?
Then came the predictive modeling part. They used tools like the Clausius-Masati equation, combined with tabulated values of Shannon's ionic polarizabilities, to estimate the theoretical K value of potentially stable multi-component oxides, things like perovskites.
Ah, so predicting the properties of more complex materials built from the stable elements. That's clever.
It was predictive material science at its finest. They were designing materials on paper before even trying to make them.
And this systematic approach, did it point towards clear winners?
It absolutely did. The analysis confirmed a key family of candidates. Among the binary oxides, zirconium oxide, ZrO3822, and hafnium oxide, HFO2, looked really good. Lanthanum oxide, LaTO33, and yttria, WaTO2O332.
HFO2, that's the one Intel eventually used, right? Hafnium-based.
Yes, HFO2 became the industry workhorse. But the calculations, interestingly, pointed even more strongly towards certain complex perovskite structures.
And the absolute standout, according to this predictive method, was lanthanum aluminate, LaLo333.
LaFal33 looked almost perfect on paper. The calculations predicted a high K, and experiments confirmed it measured values around 24-25. Remember, SiO2 is 3.9.
Huge improvement.
And it ticked all the other boxes too. Stable with silicon. Check. High band gap. Yep. 5.6 EV. Very good. Low defects. Seemed promising. It even had a decent lattice match to standard Zilla 1 silicon, only about a 1.3% mismatch.
Why do perovskites like LOL43 score so high in those K-value calculations? You mentioned something about dense packing earlier.
Yeah, it's really a structural thing. It comes down to geometry. The Clausius-Masati equation, it relates the dielectric constant K to two main things. How easily the ions polarize, alpha D, and the volume they take up, the molar volume, V dollar.
Okay.
Perovskites have this crystal structure where the ions, especially the large A and B citations like lanthanum, at least for plus, are packed together extremely efficiently, very dense. So their molar volume, V dollars, is very small.
And how does a small volume lead to a high K?
Mathematically, in the Clausius-Masati formula, this small V dollar appears in the denominator. When you have high ion polarizability in the numerator and you divide by a very small V dollar in the denominator, the predicted K value shoots way up.
Ah, dividing by a small number gives a big result. Makes sense.
Now, in reality, things like ion compression and the dense structure reduce the measured K a bit from the theoretical maximum, but that dense packing is the fundamental reason perovskites looked so good for high K.
Okay, so the theory and calculations pointed towards materials like HFO 2s2 and maybe even LOL32. But Chapter 3, it brings us back to the tough reality of actually integrating these things into working transistors. Even if you solve the stability problem, new issues pop up.
Always the way, isn't it? Yeah, Chapter 3 dives into the practical integration headaches. The first is just a general trend they noticed. There's usually an inverse relationship between K and the band gap.
Push K higher, the band gap tends to shrink.
Generally, yeah. Which means you might start getting more leakage again, defeating the purpose. It's a trade-off you have to manage.
But the really nasty surprise, the one that caused major problems once HFO22 was actually being put into production, was mobility degradation.
Ah, yes, that was a big one.
It sounds totally backward. You replace a leaky insulator with a better one, and suddenly the electrons in the channel underneath move slower. Why?
It's one of those classic unintended consequences tied directly to why these materials have high K in the first place. They rely on having soft metal-oxygen bonds. Bonds that are easily polarized by an electric field. That's what gives them high K.
Okay, soft bonds equals high K.
Right. But unfortunately, these same soft polarizable bonds vibrate easily. They act like scattering centers for the electrons trying to zip through the silicon channel just beneath the dielectric. They interact strongly with low-energy lattice vibrations, phonons.
So the electrons keep bumping into these soft spots in the dielectric above them?
Effectively, yes. It enhances scattering, slows the electrons down, degrades the channel mobility. And lower mobility means a slower transistor, which kills performance.
So the very thing that makes them good dielectrics polarizability makes them bad for electron speed. That's a horrible dilemma.
It really is, and it forced some clever engineering workarounds. The solution wasn't necessarily finding a totally different material, but modifying the high K material structure, or the interface.
How?
Well, one approach mentioned is incorporating stronger, stiffer Cialarbalo bonds into the high K material itself, creating silicates like hafnium silicon oxynitride, HHC iononolos. Those stiffer bonds are less polarizable and don't scatter electrons as much.
So you sort of dilute the softness.
Kind of. Or another common approach was to intentionally grow an ultra-thin interfacial layer of good old SiO2 to SiDoA between the silicon and the high K material, just a few atoms thick, to act as a buffer and screen the channel electrons from those soft phonons.
Interesting. This focus on structure also affected whether they preferred crystalline or amorphous films, right? The source says industry leaned towards amorphous or nanocrystalline or crystalline and amorphous, so why not perfectly crystalline films?
Primarily because polycrystalline films have grain boundaries, and grain boundaries often act as fast leakage paths for current, like little electrical short circuits running through the film.
Ah, okay. So amorphous films, lacking those boundaries, should leak less.
Generally, yes. But going amorphous introduces another problem. Dielectric relaxation, or DARG.
Dielectric relaxation. We heard that term with ferroelectrics, the slow loss of polarization. It happens in these amorphous gate dielectrics too.
It does, and it's a major headache for transistor reliability. It causes the transistor's threshold voltage, the voltage you need to turn it on, to shift over time.
Why does amorphous structure lead to DIR?
Think about SiO2. It has very rigid, constrained CP33 bonding. Not much wiggle room for atoms. But these high-K metal oxides, especially amorphous ones with transition metals, they have many more possible atomic configurations, more ways for ions and defects to shift around slightly when you apply a voltage.
So the atoms move a bit under the electric field.
And when you remove the voltage, they don't snap back instantly. They relax slowly, sluggishly, back towards equilibrium. This slow relaxation manifests as that residual polarization, the DR, which causes the threshold voltage to drift unpredictably.
And a drifting vial is a nightmare for circuit designers, right?
Yeah.
Means the transistor turns on or off at the wrong time.
Exactly. It kills reliability. Researchers had to figure out how to distinguish threshold shifts caused by simple charge-trapping electrons getting stuck in defects from shifts caused by this fundamental dielectric relaxation mechanism.
So the solution, like HFS ion dollar, was really a carefully engineered compromise.
It was amorphous to reduce grain boundary leakage with some silicon and nitrogen incorporated to stiffen the bonds a bit and reduce mobility degradation in DR, while still being thermodynamically stable as silicon. It's a material that manages to fail the least across all those critical requirements.
What a journey just to fix the insulator. It really shows how material science had to navigate this minefield of thermodynamics, mobility, stability. But fixing the charge leakage is only half the story. The other push was to rethink how electrons carry information altogether, which takes us into the spin era. Okay, shifting gears now into Chapter 4. The whole paradigm changes here. If using the electron's charge is getting too problematic, maybe we should use its spin instead. Welcome to Spintronics.
Yeah, Spintronics really emerged as a potential path forward, a way to keep scaling beyond charge-based electronics. And it offered this huge potential prize, non-volatile logic, memory that holds its state, integrated right into the processing circuits.
MRAM, magnetic random access memory, was the early workhorse here. It evolved, though, didn't it, from the first generation tech?
It did. Early MRAM used giant magnetoresistance, GMR. In GMR devices, the electrical current flows in the plane of the magnetic layers, CIP.
But that had limitations.
Scalability was tough. And the difference in resistance between the on and off states wasn't huge, so the field quickly moved to a better approach. Tunnel magnetoresistance, or TMR.
TMR, how's that different?
In TMR, the current flows perpendicular to the plane, CPP, tunneling through a very thin insulating barrier sandwiched between two magnetic layers. This structure is called a magnetic tunnel junction, or MTJ.
And why is TMR better?
Two big reasons. It scales down to much smaller dimensions much more easily. And critically, the magnetoresistance signal, the resistance change, is significantly larger than in GMR. Much clearer on versus off.
The key component there sounds like that insulating tunnel barrier. How thin are we talking?
Incredibly thin, like 1 to 2 nanometers, just a handful of atoms thick.
Wow. So its job isn't just to insulate anymore, it's actively involved in filtering the electron spins as they tunnel through.
Exactly right. And the huge leap in TMR performance, the thing that made it really take off, came from using epitaxy, growing these MTJ stacks with near-perfect atom-by-atom crystal alignment.
Epitaxial growth. That unlocked something special.
It unlocked coherent electron tunneling. Suddenly, theoretical predictions started showing mind-blowing potential MR ratios, over 1,000% resistance change.
1,000%. That's where the famous structure comes in, right? The iron-magnesium oxide iron stack. Phi 001, MG 00001.
That's the one. The physics behind that massive predicted MR is fascinating, and it relies entirely on that perfect crystal alignment and symmetry.
Tell us about it. How does MgO filter spin so well?
Okay, so in this perfectly ordered FEMGO-Phi system, the insulating MgO barrier acts like a symmetry filter for the electron wave functions. It turns out that within the MgO band gap, only electron states with a specific symmetry, called the delta duo 1 symmetry, can tunnel through efficiently. They decay slowly across the barrier.
Only the delta dotal of electrons get through easily.
Right. Now in iron, the majority spin electrons, the ones aligned with the Magnus field, have this delta dotal donegavron right at the Fermi level. The minority spin electrons have different symmetries that decay very rapidly in MgO.
Ah, so if the two iron layers have their magnetization pointing the same way, parallel,
then the majority delta 1 electrons from the first iron layer see available delta 1 states in the second iron layer. They tunnel through the MgO relatively easily.
Yeah.
High conductance, low resistance. That's the on state.
And if the magnets are anti-parallel?
Then the majority delta 1 electrons from the first layer arrive at the second layer, But now they're facing the minority spin bands, which don't have those nice delta-tilde states available at the Fermi level.
Right.
Their path is blocked, effectively. Conductance plummets, resistance shoots way up. That's the off state.
It's all about matching symmetries across the barrier. Amazing. And experiments back this up.
They did. Maybe not 1,000%, but researchers achieve really high room temperature MR values in these epitaxial femgo-tele junctions.
Yeah.
Up to around 220% reported in the source material timeframe. A huge jump from earlier TMR devices.
Okay, so femgo-feller was a landmark. But the materials search didn't stop there. Chapter 5 looks at using magnetic oxides themselves in MTJs. Things like manganites, Los RMNO33, or LSMO, or magnetite, Fe3O4.
Right. These materials are exciting because they are theoretically half metals.
Half metals, meaning?
Meaning they are predicted to be conductive for one spin direction, say spin up, but insulating for the other spin direction, spin down, at the Fermi level. So potentially 100% spin polarized current, the absolute ideal for Spintronics.
The holy grail, basically. So did these all-oxide MTJs work, like LSMO with strontium titanate STO as the barrier? Lismostalsmo?
They showed promise, but also revealed some major challenges specific to these correlated oxides. They demonstrated pretty large TMR values, like 86%, but only at very low temperatures, like 77 Kelvin.
Liquid nitrogen temperature. What happened at room temperature?
The TMR signal basically collapsed. It disappeared dramatically, often well below the temperature where the bulk LSMO material was still ferromagnetic, its Curie temperature TTLZ.
Why? If the bulk is still magnetic, why does the tunneling resistance stop changing?
It points again to the interface. In these strongly correlated oxides, the electronic and magnetic properties right at the surface or interface can be very different from the bulk. Also, the surface magnetization degrades much more quickly as you warm the material up.
Like a magnetic dead layer forms right where the tunneling happens.
Exactly, or the interface becomes disordered. Combine that with potential defect states forming in the STO barrier itself, and you lose that crucial high spin polarization right at the tunneling junction. No spin polarization, no TMR effect.
Another case of the interface being the Achilles heel. The source also mentions something really weird found in oxide MTJs, inverse TMR.
Yeah, that was a real head-scratcher for the community. They built MTJs using cobalt, Co as one magnetic layer, LSMO as the other, and STO as the barrier, Costals-Mo.
Damn.
And they found the low resistance state occurred when the Co and LSMO magnetic moments were aligned anti-parallel.
Wait, opposite to the femgo case, low resistance when anti-parallel.
Exactly. Completely inverse behavior. It totally contradicted the simple models based on the density of states of the bulk materials.
What could possibly cause that? What does it tell us about that specific Costals-Mo interface?
It strongly suggests that the electronic structure at the interface itself is dominating the tunneling process. Maybe there's some chemical reaction or charge transfer or specific defect states right at the Costo or Stolzmo boundary that preferentially allows minority spin electrons to tunnel much more easily than majority spins.
So the interface isn't just passive, it's actively changing which spins get through back.
Precisely. It implies a very complex interplay that depends sensitively on the exact combination of materials and the quality of the interface.
Okay, what about the other half-metal candidate, magnetite, Fe3O4-804? Did that fare any better?
Magnetite MTJs, specifically Fe3O4 MgO4 Fe4O4, did achieve one important milestone, room temperature operation. That was a big deal for Oxide Spintronics.
Success. But there's always a but, isn't there?
Always seems to be. The but was that the actual magnitude of the TMR effect at room temperature was tiny, really small, like 0.5%.
0.5%. That's barely measurable. Why so low if it's supposed to be 100% spin polarized?
Again, it comes down to interface quality. Suspicions fell on things like maybe the interface wasn't pure Fe3O4 maybe a dead layer formed, or perhaps competing iron oxide phases like FOMO4 which is antiferromagnetic, formed right at the boundary, killing the spin polarization just where it mattered for tunneling.
So whether it's conventional metals or exotic oxides, the story for high-performance MRAM seems to be control that interface down to the last atom or you lose the spin signal.
That's a recurring theme. And this challenge of controlling magnetic properties, especially when introducing magnetism into non-magnetic materials, leads us straight into the next section, the very tricky, very controversial world of diluted magnetic oxides.
Right, DMOs. Chapter 6 and 7 tackle this really ambitious idea. You take a standard, boring, non-magnetic oxide semiconductor like titanium dioxide, or zinc oxides, and you sprinkle in just a tiny amount of magnetic atoms like cobalt or iron or manganese.
Dilute doping, yeah.
And the hope is You create a brand new material that's both ferromagnetic, ideally at room temperature, and semiconducting.
That was the dream, a magnetic semiconductor. Imagine being able to control magnetism with an electric field or spin with voltage. It would revolutionize electronics.
But this field became contentious, is putting it mildly.
Oh, it became a scientific battlefield almost right away, especially around the most studied system. Cobalt-doped anatase, T-phobanases, Ti2O2.
What was the core argument?
For years, the debate raged. Is the room temperature ferromagnetism people were seeing intrinsic? Meaning, is the magnetism coming from the coatoms uniformly substituting for T atoms within the Ti2O2 crystal lattice, all cooperating magnetically, versus it being extrinsic? Meaning, the observed magnetism wasn't from the Ti2O2 itself, but just from tiny hidden clusters or nanoparticles of pure cobalt metal that formed within the Ti2O2 film during growth.
Basically, accidental contamination versus a genuinely new material. That distinction is absolutely fundamental.
Critical. If it's just cobalt clusters, well, that's just a dirty magnet, not a revolutionary semiconductor.
So, what was the early evidence that made people think it was intrinsic?
Well, initially, there were some pretty compelling signs. Structural studies, like X-ray diffraction, often suggested that the cobalt atoms were indeed sitting on titanium sites in the anatase lattice.
Okay, substitutional doping seemed plausible.
And there was a charge balance argument, too. Cobalt usually goes in as a 2A2 plus LaLa, but titanium is Ti4 plus LaLa. To make up for that charge difference, the material tended to form oxygen vacancies.
Missing oxygen atoms.
Right. And these oxygen vacancies can act as shallow donors, providing electrons. So people proposed this formula, like Cox die 1 Bayer 2 suggesting the Co's substitutes, vacancies form, and maybe these extra electrons help mediate the magnetic interaction between the co-ions, some kind of carrier-mediated ferromagnetism.
So the vacancies played a necessary electrical role, providing the carriers needed for magnetism. People must have been looking for a definitive test, a smoking gun for intrinsic FM.
They were, and for a while many thought the anomalous Hall effect, AHE, was it.
Anomalous Hall effect. How is that different from the normal Hall effect?
The normal Hall effect just depends on the magnetic field you apply externally. AHE is an extra Hall voltage that depends on the material's own internal magnetization. It's considered a hallmark of ferromagnetism arising from the spin-polarized carriers interacting with the lattice.
So if you saw AHE, you thought, aha, intrinsic ferromagnetism.
That was the thinking. Initially, AHE was hard to spot because the samples were often too insulating. But then some groups managed to make more conductive co-doped Ki2O2 film films, often by controlling those oxygen vacancies, and they clearly measured an AHE signal. For a time, many in the field felt, okay, debate over. It must be intrinsic.
Is the story got complicated again?
It got really complicated. Later, more detailed structural analysis, especially using high-resolution transmission electron microscopy, TEM, that revealed something disturbing.
What did TEM show?
It showed that even in some samples that clearly exhibited the AHE signal, you could still find tiny metallic cobalt clusters, sometimes just a few nanometers across, often hiding near the interface between the film and the substrate.
Wait, so you could have AHE and clusters present at the same time?
Apparently, yes, which completely muddied the waters.
How could you possibly tell if the ferromagnetism or the AHE was coming from the supposedly uniform doping or from these tiny hidden clusters?
You couldn't, definitively. That discovery was a bombshell. It meant AHE alone was not sufficient proof of intrinsic behavior. It threw the whole theoretical understanding into disarray.
The field must have fractured. Believers versus skeptics.
Completely. You had groups convinced intrinsic FM was real, driven by complex physics, and others arguing pretty much all reported room temperature FM in these systems was just due to undetected nanoscale clusters.
Okay, if the simple idea of free electrons mediating the magnetism, like the RKKY interaction, was problematic because of clusters or maybe just not enough free electrons in many samples, how did researchers explain the ferromagnetism seen in films that were actually quite insulating, films that didn't have many free carriers?
That forced the community, particularly the theorists, to come up with a totally different model, described in Chapter 7. This model works even in insulators, F-center mediated exchange.
F-centers. Those are related to the oxygen vacancies again, right?
Exactly. An F-center is basically an oxygen vacancy that has trapped 1 or 2 electrons, the electrons left behind by the missing oxygen ion. Think of it as a localized little puddle of charge bound to the vacancy site.
Okay, so how do these F-centers mediate magnetism without free electrons roaming around.
The model proposes that these trapped electrons, localized at the F center, can still interact magnetically with nearby magnetic dopant ions.
Yeah.
For example, one F center with its 2 electrons might sit between, say, 2 Cr3 plus dopant ions.
Okay.
The electron clouds at the F center overlap with the magnetic orbitals of the neighboring Chi ions. This overlap allows for a short-range magnetic exchange interaction. Basically, the F center electrons help align the spins of the nearby Psi ions ferromagnetically. It glues their moments together locally.
So it's like localized communication between magnetic ions using the vacancy's electrons as the messenger instead of needing electrons flowing through the whole crystal.
That's a good way to think about it.
What?
It provides a mechanism for ferromagnetism, even when the material itself is an insulator or semiconductor with very few free carriers.
Did they find any experimental evidence to back up this F-center model?
Yes. The source mentions that detailed studies using techniques like XAFS, extended X-ray absorption fine structure, particularly for co-doped anatase, provided supporting evidence. XAFS can probe the local atomic environment around specific atoms.
And what did XAFS show?
It showed that the oxygen vacancies were indeed located right next to the substitutional cobalt ions, structurally supporting the idea that F centers could be in the right place to mediate the exchange between them.
Okay, so after all this debate, clusters, AHE confusion, F centers, what's the sort of final verdict on DMOs from this period? Is there a consensus?
I think the consensus that emerged, as reflected in the source, is that achieving reliable, intrinsic DMO behavior is incredibly sensitive to the choice of dopant and the growth conditions. Uniformity is absolutely king.
Some dopants work better than others.
It seems so. Cobalt and iron, they just seem very prone to clustering, forming those secondary metallic phases, which makes interpreting the results incredibly difficult. The force actually points to chromium, Cr, as perhaps the best-behaved dopant in TiO2 studied up to that point.
Why chromium?
Because studies on Cr-doped TiO2 showed much more evidence of uniform Cr distribution within the lattice and much less tendency to form secondary car-metal or oxide phases. It suggested that if you can get the doping perfectly uniform, maybe intrinsic DMOs are possible. But controlling that uniformity at the atomic level is the monumental challenge.
It just keeps coming back to atomic level control, doesn't it? Whether it's dielectrics, ferroelectrics, spintronics, DMOs, it's all about mastering the interface and avoiding unwanted atomic disorder.
Absolutely, which sets the stage perfectly for the next part, where we dive into systems where these interface effects become even more dominant and complex, the strongly correlated electron systems.
All right, chapters 8 and 9. Now we're getting into interfaces involving materials where electrons really talk to each other, where their interactions dominate. Correlated electron systems. Why are these interfaces, say, between two correlated oxides, so much more complex than the silicon high-K interface we talked about earlier?
Because the fundamental physics is just richer and weirder.
Mm-hmm.
In regular semiconductors like silicon, electrons mostly act independently. You can treat them sort of individually. But in correlated systems, the interactions between electrons are strong. They can collectively decide the material's properties, whether it's a metal, an insulator, a magnet, a superconductor.
And these interactions are sensitive to boundaries.
Extremely sensitive. These materials often have very short coherence lengths, the distance over which their quantum properties remain phase coherent. Sometimes it's just a few angstroms, basically the size of one unit cell. Plus, they can host unconventional order parameters, like the weird D-wave symmetry found in high-temperature cuprate superconductors.
So the interface isn't just a simple boundary. It can fundamentally change the electronic state of the material right next to it.
Exactly. It's not just about charge accumulating or depleting, like in a simple semiconductor junction. The interface can actually trigger a phase transition in the nearby layers. This is sometimes called electronic reconstruction.
Wow. The source gives examples of this, like an interface turning an insulator into a metal, or vice versa, just by putting two materials together.
It can happen.
Yeah.
The key parameters governing these materials are things like the on-site Coulomb energy, the Hubbard U, basically, the energy cost for two electrons to sit on the same atom, and the charge transfer energy.
And the interface messes with these energies.
It can. Changes in the local atomic coordination or the electronic screening right at the interface can significantly alter the effective U, or delta dollars. For example, if the screening is weaker at an interface, the effective U might increase.
Okay, so give us a concrete example. How could an interface make an insulator metallic?
We'll take a classic Mott insulator, like nickel oxide, NiO. It's an insulator because the Hubbard U is large compared to the electron bandwidth W. But right at an interface, Maybe the coordination number of Ni atoms is reduced or screening changes. This could effectively lower the UW ratio enough to push the material across the phase boundary into a metallic state, just in those few atomic layers near the interface.
And the other way around, a metal becoming insulating at its surface.
Yep. Consider material that's metallic in bulk, like Locavio 3D3. At the surface, the atoms have fewer neighbors, which tends to narrow the electronic bandwidth W. If W shrinks enough relative to U, the UW ratio increases, and the surface layers can actually become insulating even while the bulk remains metallic.
So the interface isn't passive at all, it's actively dictating the electronic phase. Incredible. The source really highlights the high-temperature cuprate superconductors here, especially regarding their bizarre Bi-2O-Tyler wave symmetry.
Ah, yes, the D-wave symmetry. It's a cornerstone of cuprate physics, and much of what we know about it actually comes from studying interfaces, particularly grain boundaries, where two misaligned crystals meet.
This D-wave symmetry, it's not like the simple spherical swave symmetry in conventional superconductors.
Not at all. Think of the D-wave order parameter as having 4 lobes pointing along the crystal axis with alternating positive and negative signs. This complex shape has profound consequences when two D-wave superconductors meet at an angle.
And the alignment or misalignment at these grain boundaries leads to some really strange effects mentioned in the source, like spontaneously generating magnetism.
That sounds wild, but
Yeah.
yes. At certain specific grain boundary angles, the source mentions a 100 crystal, a boron-10 crystal, as an example. Something remarkable happens. First, the ability of superconducting pairs, Cooper pairs, to tunnel across the boundary is drastically reduced just due to the geometric mismatch of those D-wave lobes.
Okay, weaker coupling. Makes sense. But the weird part...
The weird part is that for certain angles, this specific D-wave symmetry forces a pi wave shift in the superconducting wave function across the boundary. It's like the phase of the superconductor gets flipped by 180 degrees just by crossing the interface.
A pi phase shift. What does that do physically?
Physically, it leads to the spontaneous generation of magnetic flux right at the grain boundary. Because superconducting currents naturally flow to minimize phase differences, this enforced pi shift can create situations where the current wants to flow in loops, generating tiny bits of magnetic field.
And this isn't normal quantized flux like in a SWID.
No, it can be unquantized magnetic flux, spontaneously generated purely by the geometry and the D-wave symmetry.
Yeah.
It's a direct consequence of breaking time reversal symmetry locally at the interface. Researchers have actually imaged these tiny spontaneous magnetic fields using ultrasensitive scanning squid microscopes.
Just mind-blowing. Generated by atomic geometry. It really drives home why transport across these correlated interfaces is so sensitive.
Absolutely. For high-TC cuprates, it means the supercurrent coupling drops off much faster with grain boundary angle than in conventional swave superconductors.
Right.
And maybe even more importantly, the roughness or atomic disorder at the boundary becomes incredibly detrimental. Any little imperfection can disrupt that sensitive D-wave pairing.
Besides symmetry effects, the source also talks about interface charging and its impact in cuprates, similar to semiconductor junctions, but maybe stronger.
Much stronger effects, potentially. Charge transfer across the interface leads to band bending and the formation of space charge layers, just like depletion layers in semiconductors. But in cuprates, a couple of factors make this effect really powerful.
What factors?
Cuprates tend to have both a relatively large dielectric constant and a low density of charge carriers compared to metals. This combination means their Thomas Fermi screening length, the distance over which charge imbalances get screened out, is very short, maybe only 0.5 to 2 nanometers. Tiny.
So the electronic structure is hypersensitive to any local charge perturbation.
Exactly. A small amount of charge transfer at a grain boundary can create a potential barrier and deplete carriers over a significant fraction of that short screening length, potentially turning a superconducting region into an insulating barrier right at the interface.
Okay, so charge transfer can kill superconductivity locally, but then the source says something really counterintuitive. Sometimes doping the interface in cuprates can actually improve performance. That seems backward.
It does seem backward based on conventional superconductors, where you want interfaces to be as clean as possible. But in cuprates, it can work. The source describes experiments where they intentionally doped grain boundaries, for example, by substituting some calcium for yttrium in YbO2Cu3O7 delta, YbCO, right near the boundary.
And that helped. How?
It significantly enhanced the critical current that can flow across the grain boundary. The thinking is that the calcium doping helps to reduce the height of that detrimental potential barrier caused by charge transfer and band bending, or maybe narrows the width of the depleted region.
So instead of just accepting interface problems as inevitable, the complexity of correlated systems allows scientists to use doping, almost like an engineering tool, to actively counteract the negative effects of the interface physics itself.
Precisely. It's atomic-level tuning made possible and necessary by the complexity. The interface isn't just a passive boundary. It becomes an active component you have to engineer to get the device function you want.
This focus on engineering interfaces, on controlling things atom by atom, it leads us perfectly into the final part of our deep dive, the advanced fabrication techniques that are making all this possible. Okay, Chapter 10 shifts focus slightly to a different application space, wideband gap optoelectronics, specifically looking at zinc oxide, ZNO. Why is ZNO getting attention here?
ZNO emerged as a really interesting candidate for things like blue or UV LEDs and detectors. It has a direct and wide band gap, which is what you need for efficient light emission and detection in that part of the spectrum.
And it plays well with existing technology.
That's a big plus. Structurally, ZNO is quite compatible with gallium nitride, JN, which is already a major material for blue LEDs. The lattice mismatch is small, only about 1.9%.
So you can grow ZNO on top of readily available GaN on sapphire wafers. Use them as high-quality templates.
Exactly. It opens up possibilities for hybrid devices combining the strengths of both ZNO and GaN. But, like with most complex oxides, actually growing high-quality ZNO films, especially using pulsed laser deposition, PLD, turned out to be a tricky optimization problem.
What was the main trade-off they ran into with PLD growth of ZNO?
It came down to the oxygen pressure in the growth chamber during deposition. There was this fundamental conflict.
Okay, what happened at low pressure?
If you used very low oxygen pressure, say around 10 ticks torr, you could get films with excellent epitaxial quality, really nice crystal structure, well aligned to the substrate. But the surface morphology was rough, lots of little islands.
And a rough surface is bad if you want to stack layers, like for a quantum well.
Death sentence. You can't grow smooth, uniform layers on top of a rough surface. Okay, so then you try high pressure.
What happens at high oxygen pressure, like $10 Thor?
At high pressure, you got nice, flat, smooth surfaces, great for building layered structures. But those films had problems. Poor electron mobility, high density of defects, probably because the excess oxygen filled up beneficial vacancies or created scattering centers. The optical and electrical properties weren't as good.
So you couldn't get good crystal quality and a smooth surface at the same time in a single growth step. Classic materials science problem.
Yep. So the solution, which you see often with these sensitive oxides, was to use a two-step growth process.
How did that work?
First, they'd use the low-pressure condition, 10-6 sort, to grow a thin initial nucleation layer. The goal here is just to get the crystal structure right, perfectly templated off the substrate, get that high-quality epitaxy established.
Okay, good base layer. Then what?
Then they'd switch to the high-pressure condition, 10-3 torr, to grow the rest of the thicker film on top. Now the priority is getting that smooth surface morphology. The underlying nucleation layer helps maintain decent crystal quality.
And this two-step combo, it gave them the best of both worlds.
Pretty much. The source says this method allowed them to achieve superior epitaxy, smooth surfaces, high electron mobility, and good optical properties all in the same film.
Yeah.
Absolutely crucial if you want to make things like quantum wells or superlattices.
Makes sense. Now, beyond just pure ZNO, researchers often need to tune the electronic properties, like the band gap. Alloying is the usual way, right?
Right. For ZNO, they looked at alloying it with magnesium oxide, MgO, to create ZnGO alloys. Adding mag gap pushes the band gap wider, potentially up to around 3.9 EV, useful for tuning the color of light emission or detection.
Another problem. Alloying isn't always straightforward.
Not here, no. They ran into a structural hurdle at phase separation. ZNO has a wurtzite crystal structure. MgO has a cubic rock salt structure. They're fundamentally dissimilar.
They don't mix well naturally.
Not really. Thermodynamically, they have very limited solid solubility. If you try to grow ZNMG way, using slow, conventional methods that stay close to thermal equilibrium, the Mg would just tend to separate out into its own MgO phase, ruining the uniformity and properties of the alloy film.
So you couldn't just slowly cook them together. You needed a way to force them to mix to overcome thermodynamics.
Exactly. And that's where a technique like PLD becomes really valuable again. PLD is inherently a non-thermal equilibrium growth technique.
How so?
Because the material arrives at the substrate in these very short, high-energy bursts from the laser plume. It doesn't have much time to settle into its lowest energy state, which would be phase separation. This rapid quenching effect allows you to trick the material into forming a solid solution with much higher Mg content than the equilibrium phase diagram would predict.
So PLD speed helps suppress that unwanted phase separation.
Critical for making these tunable xenon MgO alloys across the composition range needed for optoelectronic devices. It highlights how the growth technique itself enables new materials.
And this need for non-equilibrium growth, for precise control over composition and structure. It leads us right into the final chapters, discussing the really cutting-edge tools developed for discovering and fabricating these complex oxide-thin films. Okay, let's start with Chapter 11, Combinatorial Synthesis. This sounds like a way to do materials discovery much, much faster.
It really is. Combinatorial PLD is an incredibly powerful technique for rapidly mapping out how a material's properties change with its composition. Instead of making dozens of separate samples, you create a whole range of compositions all on one single chip.
How do they do that? How do you create, say, a smooth gradient of BO1 Serixtitio 303s across one substrate using PLD?
It's a clever setup using synchronized shadow deposition. Imagine you have two PLD targets, one of BDO 300 BTO and one of Surio 300 STO. You rapidly alternate firing the laser at each target.
Okay, alternating pulses of BTO and STO material flying towards the substrate.
Right. Now you place a moving shutter or mask with a specific opening between the targets and the substrate. This shutter moves back and forth in sync with the laser pulses.
So the shutter blocks part of the plume.
Exactly. It's designed so that one end of the substrate gets hit by many more BTO pulses than STO pulses, while the other end gets hit by many more STO pulses than BTO pulses. And in the middle, it's roughly 50-50.
Ah, creating a gradient in the BTO to STO ratio across the substrate.
Precisely. And crucially, they deposit only a tiny amount, less than a single unit cell layer, for each pair of BTO pulses. They repeat this cycle hundreds or thousands of times.
So that rapid alternation forces the barium, strontium, titanium, and oxygen atoms to mix together really well at each point, forming a continuous alloy gradient.
Yes, it creates a pseudo-binary composition spread. And then comes the fast characterization part. For that Banatelli 3.3 example, they used a scanning microwave microscope.
To measure what?
To measure the dielectric constant point by point across the entire chip, mapping K as a function of the composition X.
And they found the sweet spot.
They found the dielectric constant peaked around the composition BNOL 65 SA array 0.35 TO33.
Which matches known properties.
Perfectly. That composition is known to have its ferroelectric to paraelectric phase transition, where the dielectric constant peaks right around room temperature. So instead of months of work making individual samples, they basically mapped the phase diagram in an afternoon on a single chip. Hugely efficient.
Incredible speed up for discovery. But discovery isn't enough. You need precise control during growth. That brings us to Chapter 12 and real-time monitoring, particularly using high-pressure R-read.
R-read reflection, high-energy electron diffraction. Yeah, that's been a standard tool for monitoring thin film growth in ultra-high vacuum, UHV, for ages. Gives you real-time info about the surface structure and smoothness.
But the problem is, many complex oxides, especially when grown by PLD, need a significant background pressure of oxygen to get the stoichiometry right. And R-read uses an electron beam.
And high-energy electrons scatter like crazy off gas molecules. So standard R just doesn't work at the oxygen pressures needed for growing many oxides, which could be up to, say, 50 Pascal. That's way too high for a normal electron beam.
A fundamental conflict. How did they solve it? How do you get RHE to work at high pressure?
The solution was clever engineering, differential pumping. Basically, you create multiple vacuum stages between the electron gun, which needs to be in high vacuum, and the growth chamber, which is at relatively high oxygen pressure.
Like airlocks for electrons.
Kind of. You use very small apertures connecting the stages and powerful turbopumps on each stage. This allows you to maintain a huge pressure difference, keeping the electron gun happy in vacuum while the beam passes through the small apertures into the higher pressure chamber, hits the sample, and the diffracted electrons come back out through the apertures to the detector.
An engineering feat. And this allows RHE to operate right up to PLD-relevant pressures.
Yep, up to tens of pascals. It means you can finally watch oxide growth happening layer by layer in real time under realistic conditions.
What exactly are you watching? You mentioned RET intensity oscillations earlier. What do those tell you?
Those oscillations are the gold standard signature of 2D layer-by-layer growth. Here's how it works. Start with an atomically smooth surface, high R8 intensity. When you deposit the first bit of material, tiny islands start to form. The surface gets rougher on an atomic scale, scattering the red beam more diffusely, so the intensity drops.
Okay, intensity drops as islands form.
Then, as deposition continues, these islands grow and merge together. Once they completely cover the first layer, the surface becomes atomically smooth again, and the red intensity shoots back up, completing one oscillation.
Ah, so one full oscillation corresponds to growing exactly one atomic monolayer.
Precisely. By tracking these oscillations, you can measure the deposition rate with incredible precision. But even more importantly, you can see how long it takes for the intensity to recover after each pulse. That tells you how long the atoms need to rearrange themselves and smooth out the surface.
And having that real-time kinetic information, it actually enabled a whole new way of growing films. The source calls it pulsed laser interval deposition, or PLAID.
PLID is really where real-time monitoring enables atomic-level engineering. The REG monitoring showed that after a typical fast PLD pulse deposits material, those atoms need a certain amount of time and interval to relax, diffuse around on the surface, and find their proper crystal sites before the next pulse arrives.
Okay, they need time to settle down.
Right. Now, under some growth conditions, like high deposition rates or lower temperatures, the atoms might not have enough time to form a complete smooth layer before the next pulse hits. You start nucleating islands on top of islands, multi-level, 3D growth, leading to rough films.
So PLID uses the RAG feedback to prevent that.
Exactly. PLID uses intentionally short, fast laser pulses to deposit maybe just a fraction of a monolayer, followed by a relatively long interval, maybe half a second or so, with no deposition. This pause gives the atoms the time they need to fully reorganize and recrystallize, forcing the growth into a layer-by-layer mode, even under conditions where it would normally roughen up.
You're using a high-tech pause button, timed perfectly using RAG infrared to maintain atomic smoothness.
That's the essence of it. It allows for incredible control over interface quality, which, as we've seen over and over, is paramount for almost all these advanced oxide devices, ferroelectrics, MTJs, correlated heterostructures.
And this level of control is confirmed in systems mentioned in Chapter 13, like PLD MBE setups with integrated RHE, where they show TEM images of atomically sharp interfaces in complex superlattices like body OV3 through TO3, KDO3.
Yes, those images are the ultimate proof of the control achieved. Chapter 13 also touches on a few other advanced pulse deposition techniques. One is ion beam-assisted deposition, or IB. That sounds different. It's not just about depositing material. No, IBID is about actively controlling the crystalline orientation of the growing film, even if the substrate itself is poorly ordered or randomly oriented.
How does that work? You're hitting the film with ions while it grows.
Yes, you have your deposition source, could be PLD, could be sputtering, but simultaneously you direct a low-energy ion beam at the growing film, hitting it at a very specific angle.
Why a specific angle?
That angle is chosen to correspond to a channeling direction in the desired crystal structure. Ions traveling down these open crystal channels cause less damage, so crystallites that happen to be oriented along that channeling direction tend to survive and grow preferentially, while grains with other orientations are damaged or sputtered away by the ion beam.
So the ion beam selectively prunes away the badly oriented crystals, letting the well-aligned ones dominate. It imposes texture.
Exactly. It imposes biaxial texture alignment both in plane and out of plane onto the film. And the really killer application for this, mentioned in the source, is huge.
What is it?
Depositing high-quality, high-temperature superconducting YBCO films on cheap, flexible, randomly oriented polycrystalline metal tapes.
Wait, not on expensive, perfect single crystal substrates, on regular metal tape?
Yes. IBE allows you to create a highly textured buffer layer on top of the disordered metal tape, and then you can grow the YBCO superconductor epitaxially on that buffer layer. It completely overcomes the substrate limitation.
And the performance?
They achieved fantastic critical current densities, over 1 million amps per square centimeter on these flexible tapes. This basically enabled the whole field of second-generation superconducting wires for power transmission, magnets, etc. A massive breakthrough driven by controlling texture with IBA.
Truly materials integration at its most impactful. Okay, one last technique mentioned. Pulsed electron deposition, or PED. What's the angle there? An alternative to lasers.
Potentially, yes. PED emerged as a possibly cheaper, more scalable alternative to PLD for depositing complex materials, instead of using a big, expensive, often inefficient excimer laser.
It uses electrons.
It uses a high-power pulsed electron beam, typically generated by something called a pseudo-spark discharge. These electron beam pulses can deliver energy densities comparable to pulsed lasers, enough to ablate target materials and create a plume for deposition.
What are the potential advantages over PLD? Why explore this?
The main drivers are cost and efficiency. The electrical energy-to-beam energy conversion efficiency for these electron beam sources can be much higher, maybe up to 30% compared to only around 3% for a typical excimer laser.
Wow, 10 times more efficient. That should translate to lower running costs.
Potentially lower capital costs for the equipment too. Plus, how electrons deposit their energy in the target material is sometimes less sensitive to the material's optical properties compared to photons from a laser, which might offer advantages for certain materials or smoother plume generation.
Has PED actually been shown to work for complex oxides?
Yes, the source notes it was successfully demonstrated for materials like superconducting YBCO, achieving critical current densities comparable to state-of-the-art PLD films. So it definitely showed promise as a viable, potentially more manufacturable pulse deposition technique.
What an incredible tour of fabrication technology. It really feels like the ability to build these materials atom by atom is just as important as discovering them in the first place. Hashtag outro.
Absolutely. Looking back across all these chapters, all these materials, the single biggest takeaway has to be that Oxide Electronics is this new frontier defined by controlling what happens at the nanoscale, especially at buried interfaces.
Oh, yeah, that interface theme just came up again and again. And the physics there, it's often way more complex, way different than what happens in the bulk material.
Totally. We've really moved beyond just looking for one single material to replace silicon dioxide or one material from memory. The cutting edge now is designing these complex, multifunctional heterostructures, stacks of different oxides where the final properties are literally synthesized, engineered layer by atomic layer.
And the physics we encountered, F-center exchange in DMOs, that crazy orbital filtering in MEMGEO tunnel barriers, spontaneous magnetic flux from D-wave symmetry, it's just far more intricate than your standard semiconductor physics.
It really is, which demands a whole new level of understanding and control.
Reflecting on this whole deep dive, from the SiO2 crisis right through to PCD, what really stands out to you as the most significant thread?
You know, besides the complex physics, I think the parallel evolution of the tools is just as compelling. High-pressure RHED letting us watch atoms stack up in real time. IBAD letting us impose crystal order onto chaos. Combinatorial methods letting us discover optimality incredibly fast. PLID letting us force layer-by-layer growth.
It shows that mastering the fabrication process, getting that atomic-level control, is every bit as crucial as the initial materials discovery. They're inseparable now.
They have to be. Success is measured by how well you can control atomic disorder, especially at those critical interfaces.
And when you look at the materials that consistently popped up as the most promising things, like lanthanum aluminate, lanthanol 3D3 for dielectrics, bismuth ferrite, BFO for ferroelectrics, the manganites for spintronics, they're often these complex perovskite oxides.
Structures known for being incredibly sensitive to stoichiometry, strain, defects, those interface effects we discussed.
Right. They offer amazing potential functionality, but maybe they come with an inherent fragility.
And that fragility leads directly to, I think, the final provocative question we should leave the listeners with.
Okay, what is it?
Given how incredibly sensitive these complex oxide structures are to atomic level disorder, whether it's a single oxygen vacancy acting as magnetic glue, or a tiny step at an interface disrupting D-wave pairing, or dielectric relaxation shifting a threshold voltage. How on earth are we going to guarantee the long-term reliability and stability of these materials when or if they finally get scaled up into devices with billions of components?
Yeah, making one perfect interface in a lab is one thing. Making billions of them identical and stable for 10 years in your phone.
Exactly. The future success of Oxide Electronics doesn't just hinge on demonstrating exciting new physics or functions. It ultimately rests on whether we can achieve and maintain near-perfect atomic order and mitigate the effects of the unavoidable defects across billions of transistors, billions of memory cells, over billions of operating cycles. That challenge, guaranteeing atomic scale perfection and stability at massive scale, might be the biggest hurdle still ahead for this entire field.